Okay, so in this one, what I want to do is go through some of the maths skills that you need for the GAMSAT exam, particularly how to tackle complex calculations really quickly without a calculator. I've gotten a lot of questions asking about like what kind of maths is involved. People are talking a lot more about it being much more maths heavy as well with the new kind of format. So this will basically be running through some of just the high frequency stuff. It's not going to be absolutely everything. This is just based on what I've seen in the ACE material and then also what was in the actual sitting as well. It's ultimately not a maths exam though, so questions aren't going to be explicitly about solving equations all the time. There's going to be some reasoning behind it as well, but the use of maths to be able to reason out questions is going to run through, and it's quite common obviously in the physics questions. It's very common in the chemistry stuff, and it's becoming more common in the biology content as well now, although the majority of the biology questions are much more about graph reading and analysis and that kind of thing. So what we'll do is I'm just going to run through a structure of some of the different types of problems that you run into, and then some different strategies for how to tackle them. So the first one I think is dealing with decimals, right? And having to do basic computation with decimals without getting flustered or overwhelmed. I can see that there's a bit of a trend in the questions where the calculations themselves are doable, but they're testing to see if people are going to think clearly under pressure. So if you start to kind of ham up over it, you'll probably kind of hyper focus on the actual values themselves and the specific calculations. But obviously it is a multiple choice test, and most answers, especially when it comes to calculation, are about which is closest in value. So one of the first things that I would actually do before I even get to the calculation is I would scan the four options and work out how much margin of error I have. So a common one is that, let's say we're calculating something in joules, and you'll see that one answer is 10 joules, another one's 100 joules, another one's 1,000 joules, and another one then is like 10 kilojoules or 10,000 joules. So there's a factor of 10 between each of them, and that's a pretty big margin of error. In saying that, lower down here, for example, these are relatively close in the scheme of the other two. So I wouldn't be confident immediately just ballparking it without any calculation, but it does give me some leeway in knowing that I don't have to be perfectly accurate, because my answer should, even with a bit of error in estimation, fall close to one of these four numbers pretty conclusively. So that's the very first strategy. The second thing that I would go through is with the calculations, whenever there's decimals, try to avoid actually dealing with the decimals if you can avoid it. So a really common formula that comes up is the gas law in chemistry questions, PV equals nRT, and they kind of explain it every time. There's no need to necessarily memorize them, although if you've done a science course or anything, you've probably got that one kind of drummed in. So what we do here is, first of all, make sure that you're in standard units for the calculations. So remember that pressure measured in kilopascals, volume in liters, N being in mole, and temperature being in Kelvin. A lot of people get that one jumbled and put in the degrees Celsius, and R is always stated, so 8.314, they may round it. And this right here is the example of where you have some trouble coming in, right? So you got this really specific decimal, but you can usually avoid it because your answers are going to be relatively spread out or different. They're going to know if you've tackled the question correctly. They're not as fussed about your ability to do computation to the nth degree. They just want to see that you can reason it and then understand what kind of mathematical process to take. Beyond that, if you've taken that, you should then lead to the right answer. So they're looking for a level of accuracy, but beyond working with whole numbers and actually problem solving it, working with decimals is just not really the skill they're trying to look for. So if we had something where, say, we were trying to solve for the temperature, and we were given, say, a number of mole of 0.81, and then the volume was going to be, 3.02 liters. This is in moles. The pressure, let's say it was 1 atmosphere, so 101.3 kilopascals, and then the R is already given. And so let's say they were asking for temperature. So the first thing I would do is rearrange the formula before you put the numbers in takes up less space on the scrap paper that you're given or that you've got to work with. So first thing is we can just divide RT across as a big lump. So PV on RT, and then we plug our numbers in and see what we're dealing with. So pressure, 101.3 kilopascals, multiplied then by the volume, 3.02, and then divided by the R, which is 8.314, and then times by the temperature, which I just realized to stuff that up. Let's change that. Let's say the temperature, let's say we don't know the number of moles, and we're given the temperature as like 25 degrees Celsius, so 298 Kelvin. And so we'll put 298 down there like that. Just to make it so I don't have to go back through it. Doesn't really matter, skill's exactly the same, right? And so we can see every single number is horrible in terms of dealing without a calculator. But in the grand scheme of things, against 100, lopping off the 1.3 is a tiny, tiny proportion. So always look at the amount of estimation you're making relative to the size of that value, right? And I mean, look, generally speaking, I wouldn't knock off more than 5%, but I wouldn't sit there necessarily going, oh wait, what's 5% of that number, blah, blah. But they're 1.3 on 101.3, not gonna make a big enough difference. So we're just gonna call that 100. This, again, same thing, 0.02, let's just call it 3. And over here, this is probably the trickiest one. I might leave that as 8.3, but beyond that, it seems insignificant, and just see if I can get as accurate as possible. And 298, again, I'm gonna call that 300. And by doing that, you can then start to cancel stuff out way, way easier and start to see the patterns in things. So here we've got a couple of zeros that we can knock out like that. The 3 can go with this 3, and we end up with 1 over 8.3, like that. And so again, what I would do here is go, well, 1 over 8 is a whole lot easier, 0.125. So if you divide it by 0.3, it's going to be a little bit less than 0.125. So I might say 0.122 or something. And then I should have a pretty close approximation at that point. In fact, the answers should be far enough that that is either right on the answer or it's very, very, very close to just 1. And so already that kind of breaks down without a calculator. You can move very, very quickly. You can see that what it's actually assessing is, do you understand the concepts of the chemistry? And then are you confident with manipulating formulas? Whether or not you can multiply and divide decimals in your head like a calculator is completely useless to them, right? That's not at all what they're trying to assess. So you can usually skip past all of that. The next thing is looking at how to rearrange formulas. So obviously I can't go through every single combination of possible formula, but they do, most of the time they're pretty straightforward. It's just a lot of multiplying, dividing, square roots, that kind of thing. But some common pitfalls, and you may already be familiar with these, so I apologize if this is a bit repetitive, just skip past it to the next timestamp. But if we had something like, for example, x on a times 1 on p plus 1 minus h is equal to k, and the goal is to solve for p. That's probably about as bad as it'll ever get, right? And this is not a real formula, I've just made it up. So my goal here is to get p on its own, right? Everything that is kind of attached to it needs to move to the other side, right? And a general rule of thumb is move the stuff that is furthest away from it, right? And we'll just see where it heads. So first of all, I can see that the minus h needs to move, so let's dump that over here. So we've got x, I'm gonna leave x on a separated because I'm gonna move it as a big chunk. So I get k plus h. Next up, then what I can do is I can divide the x on a across, reversing that time. So 1 on p plus 1 is equal to, I'm going to divide this across, but in order to do that, make sure that looks like a h, I'm going to times and flip the fraction. So it'll be, that's the same as dividing by x on a. That just cleans it up a little bit. And then lastly, without even working out what this is, I need to put that in brackets, I'm just going to switch out this one here with this whole lump over here. Remember, if it doesn't have p in it, it can move all together. So this would be 1 on k plus h multiplied by a on x is equal to p plus 1. And then I know to just minus 1 from it. Now, sometimes it's a case of making the expression look the same as they've expressed it. So then you have to manipulate a little bit further. So always be on the lookout for that. But I mean, there's not a huge amount more that we could go here. I could probably pull out, so k plus h times a, put the x down there, take away 1, and then I can kind of flip this fraction, so 1 and then times by x on a. That looks a little bit nicer. And then that would give me x on a times k plus h minus 1 is equal to p, and that's probably as far as they're going to go, right? They could potentially put this over the same denominator, but that would start to make it a whole lot messier. So the goal is always going to be move what is furthest away from the letter that you're trying to solve, and generally speaking, if it doesn't have that letter in it, you can move it as a big lump all at once. The less moves you have to make, the quicker you're going to be, the less space that you take up on the paper as well. The other trick as well is, as I said before, don't put the numbers in until you've rearranged it. It's usually a little bit easier to deal with because you're not overwhelmed by all the numbers that are dumped in, and it's faster to write because you're just writing letters, right? And it allows you to see the connections a little bit more as well. So that's the other thing. So that's with rearranging and manipulating formulas. The next then is looking at your index laws. So index laws are used very frequently. I'd say that's probably the most frequent math skill that you'll use throughout it. And it's no different from high school maths, but it may need a bit of a brush up. So the first thing is we've got a bunch of different laws. So we'll go through them, and again, skip if you're already familiar with them. But basic patterns are, if you're timesing two indices or index forms, then you can add the indices or the powers. If you're dividing them in some way, then you subtract them. If you're raising powers, doesn't happen too much in GAMSAT, to be honest. You multiply those two individual powers. Anything to the power of 1 is equal to itself. Anything to the power of 0 is equal to 1. And then negative powers means they're unhappy. They want to flip to the other side of the fraction. And if we have fractional powers, that refers to a cert. So I always remember that the bottom number remains the bottom. So n stays down low, the nth root of a, and then you raise that answer to the power of m, like that. It is interchangeable. You can also put the m as the power inside. I prefer this method. They both give the same answer because it tells you to root the number first and then raise it. And that'll mean that you stay in small numbers by rooting it first. Whereas if you raise it to the power first, it's going to blow out to a large number and it's going to be hard to deal with. Cool. All right. There are obviously analogous log laws that relate to this as well. So for every index law, roughly, there's a log law. So where we multiply and add here, when we add two logs of the same base, then we can write them as one base or one log, and we just multiply. So you can see multiply, then add, then multiply. It's just in reverse. If we subtract two logs, like this, then it's the same thing as one log where we divide the two values. Then this one, the equivalent of raising powers, it's actually used quite frequently, to be honest, is if you've got log a of m to the n can jump down the front and it can switch back and forth. You can't apply log laws with a coefficient out the front, so often you'll actually see it written in this form, n times log a of m, and it means reverse the law, raise it back to the power, and then you should be able to apply other log laws to solve the problem. The log a of a is equal to 1. Log a of 1 is equal to 0, and log a of 0, or really log a of anything less than 0, is undefined. There's no answer. You can't raise something to a power and make it or at least you can't raise a positive number to a power and make it negative all of a sudden, which is why that one exists. Probably won't come up. That's more maths heavy than it is GAMSAT and science related. And there we go. So those are all the index and the log laws. We use the logs and indices probably most when it comes to radioactive decay questions and radiometric dating in biology questions for evolution based stuff, or it could be used in radiation in a physics-based question. And so they usually tell you, for example, the natural log value of 2. They don't expect these, and the natural log value of a half, which if I remember correctly is 0.693. They will give you that, and then you'll work with that. And again, that's just a decimal that you can deal with. So you could estimate it to be 0.7. You could also say that's 7 on 10 to get rid of decimals altogether, like that. A lot of the times though, you're not actually even needing to deal with the decimal. You're doing things in terms of that log itself, right? So they might have something, obviously this is completely made up, but it could be something like, 3 natural log of half x equals 4 or something like that. And then they'll say, hey, solve x for us, right? So what you could do is you could use some of your log laws. So you could divide the 3 across. This is very specific, so very unlikely to actually be asked in this way, but it's just to prove the point. 4 on 3. And at this point here, you could apply 2 log laws. So you could go, oh, okay, well, that's the same as log of half plus log of x, right? Reversing that first log law is equal to 4 on 3. And we already know that log of half given in the question is 0.693 plus natural log of x is equal to 4 on 3. We'll come over here. So therefore we can solve for natural log of x is 4 on 3, take away, let's call it 0.7. 4 on 3 is 1.3, take away 0.7 is then going to be 0.6. And there's the natural log. And then x here might be e to the 0.6, right? Or e to the 6 on 10 or something very, very close to that. So they're all 3/5 in fact, like that. So that brings me then to another thing, which is when you're switching between logs and exponentials, easiest way to do it is, at least this is the way that I always teach it, is base to the answer is equal to the bracket. It's a very non-mathematical way of thinking of it. And the idea is that the equivalent is a log with a base down here. The bracket is the thing that goes in the brackets. And the answer is the answer. So you can see over here where we had natural log of x, that is log with a base e, Euler's number of x is 0.6. So I just went, well, base, so e to the power of the answer, 0.6 is equal to the bracket. And that's the equivalent exponential. And then I can solve for the thing in the bracket. Like that. And there we go. Cool. Another really handy tip is being able to estimate certs quickly in your head. And so obviously a lot of the times you get things like the square root of 16, cube root of 125 or something, and you can just get them as whole numbers. But it's worth knowing how to estimate ones that fall in between. So let's say we had to do, for example, start with a simple one, the square root of 15. So what I would do is go, well, if I'm trying to do the square root, I'm first going to think like a number scale. What's the perfect square that sits just below 15? And that would be 9. The perfect square that sits immediately above 15 is 16. I'm going to put 15 on my scale, which should sit about here or so. And then I go, all right, the square root of 9 is 3, and the square root of 16 is 4. So even though this is not a linear scale, you can get a rough approximation. The basic idea of a cert is that it exaggerates the extreme ends, so it'll push itself closer towards either of these values, and it won't push towards the middle quite so much. There's no point being really specific and going, oh, that's 1 increment out of a 7 increment scale, so 1/7 times, blah, blah, blah. You don't have to do anything like that. I would just estimate roughly, because remember, it's all an estimating game. And so I would go, okay, it's going to be a little bit less than 4. I might say 3.9. It could be 3.8, could be 3.78 or something weird like that. 3.9 will do, right, for the calculations. There we go. And you can do that for anything. So if you wanted to do the cube root of 65, then you know that, the cube root of 64, for example, is 4. And the next one, I guess 5 cubed is 125. So 65 is very, very close to here. So the answer should be like, 4.1, maybe 4.01 or something like that. So you can effectively call it 4 for your calculations. So the other one, it's probably worth just knowing how linear equations work. Less likely to come up, but it's possible that you could have to use some kind of linear approximation tool for a graph analysis. So say that we had a graph like this, and then they might say that this occurs at something like day 10. Who knows what this would be? Maybe it's like viral particles in the bloodstream or viral particles in the system or something like that, and it's growing exponentially. If they then said the rate remains constant from day 10 for another 20 days, how many viral particles would be showing. What you do there is draw in a tangent line at that point. Let me do that again. So you try to roughly predict the gradient, which maybe looks around about like that. And then this actually becomes your equation, and you'd have to work out what the equation of that line would be very, very quickly. So you'd already have this point here. Let's say that is 10 and 200. And then you'd have to use the grid lines and work out where that line passes. So you'd have to use a straight edge. The good thing is it's a screen test, so you could just hold the edge of the paper up as your ruler, in a sense, and try to read the points off of it. And so let's say we get a point here that isn't quite reaching to 20, but it's like 12, and it says 240, like that. Then from there, you can get the gradient. So the gradient would be good old y2 minus y1 over x2 minus x1 from high school, if it rings any bells. 240 take away 200 over 12 take away 10, right? So 40 take away divided by 2, which gives you a gradient of 20. And then, you know, the equation is going to be y equals 20x plus c, the y-intercept. And we need to sub in a point to solve c. So I like to sub in the lower points. So we're going to sub in 200. It's 20 times 10. That'll force out c, and we get 180 for c. So then we've got y equals 20x plus 180, and then we can extrapolate that and put in day 20 at that point, right? As the question would have asked. And then we get 400 plus 180, or 580 particles. And again, estimation tools, right? So if there were decimals in there, it was like 17 instead of 20 and that kind of thing. Just call it 17 or 15, whatever you're more comfortable with. Get a ballpark and see if you can actually get it a clear, conclusive answer. And so then particularly for physics questions, they have a lot that rely on proportionality. So we're going to go through how to deal with proportionality really quickly. So let's say they give you the formula for principles of gravitation, and they say that a gravitational force, in fact, no, let's do gravitational field strength, because they seem to love gravity, is given as Gm on r squared. And they tell you everything. They say G is a gravitational constant, 6.67 by 10 to the negative 11. Capital M is going to be the mass of the object, or the planet, or the planetary body that we're measuring its field of. And then R is going to be the radius, or the distance from the center of the planet. And they usually explain this. They don't expect people to be familiar with this formula, although it is like introductory physics, and many of you may be already familiar. They do re-explain this. So if I draw, that's not really going to work. Let me try that again. Yeah, we'll have a bit of an oval-shaped planet. That's fine. And so, actually no, because we need it to be a circle. I'll do my best to get a circle here. Okay, that's much better. All right, and so here we've got the center at this point here, and this would be the radius of the actual object, but what we're looking at is measuring the gravitational field strength at some distance over here. So let's say we're standing here, and then this would actually be our R value, and it's not from the surface. So if they talk about surface and altitude, altitude is only measured from the surface of the object. That would mean you have to add the radius of the planet, and they would have to give you that in the question. Cool. So if we're trying to do that, obviously we could just plug in and we could calculate the gravitational field strength, or we could solve for a mass given the gravitational field strength. What we care more about in this is what happens when we actually change these variables. So if it said something about, you know, doubling the distance of the person from the center of the earth, right? So they double their distance from here out to here instead, position number 2, position number 1. They've effectively doubled their radius then. What happens to the gravitational field strength? So rather than actually plugging in the formulas, you can just go, well, if G is equal to Gm on r squared, then we can say a proportionality statement, and anything that is remaining constant or is a constant becomes a 1. So G is a constant, so that'll become a 1 in a proportionality statement. M is not changing because it's still the same object in this case, so that is not a variable, that becomes a 1. The R, on the other hand, is changing, and what you put in is the factor of change. So not by how much it increased, but by the factor that it multiplied itself by. So in this case, we doubled it. So that would mean we put a 2 in its place, and we apply any maths to it as well. And in this case, it was squared, right? So we have an inverse squared relationship, and we can work out the factor impact on the gravitational field strength, and it's going to be 1 on 4, right? So what that means is G goes to a quarter of its size. Another way to say that is a 75% reduction. They could play around with percentages as well. So if it's equal to a quarter of its old size, it's lost 3/4 of its old size as well. Then if they do combos where they're changing multiple things, let's say that for whatever reason there's like, I don't know, some kind of an explosion or something, and a whole bunch of the density or the mass of this planet disappears and it becomes much, much lighter, and its mass goes to a fifth of its old mass. So the mass now is going to be a fifth of the initial mass. We're going to also then, let's say the blasted us further away from the object as well, and we went to, our radius went to 3 times our initial radius. And then we want to work out what happens to G. So again, we could just apply that. G, capital G is a constant. The mass now we put in 1/5. Divide that by, now we put in a 3 for the radius, because it went 3 times greater. We square it, and we see what the factor of change is. So at the top we get 1/5 over 9, which is 1 on 45. So effectively G went to a 45th of its value. Now other ways that they could play around with that is they could say roughly what percentage of its old gravitational field strength does it now possess at this particular radius. And that would be 1/45th, which is kind of like 1/50th, which is kind of like 2%. So that's a little bit less than 50, so it should be a little bit higher than 2%. So they might have one answer that says 2% and another one that says like 2.1% or something like that. And the idea is that we're going for the most correct. So even if you haven't done an exact calculation, you know that a little bit higher is probably going to be more accurate than the complete estimation of 2%. There we go, and that's how we can do proportionality. So it avoids having to actually plug in the actual absolute values. You can just deal with factors of change, and then you can trace what actually happens to it as well. Cool. All right, hopefully that was helpful. I'm probably going to do another one, so if there's anything that I've missed or anything that you still want to see in another video, then just let me know. I can do a second round if it's needed. These, I think, are the most common math skills that are used. A lot of it is based on your ability to manipulate maths either in your head or on paper really quickly without having to write a whole lot. And the idea is that these skills are there to save you space and time so that you can answer questions more confidently, so you don't have to fall into guessing or anything like that. All right, cool. So the third edition of Thursday Thoughts is coming out this Thursday. If you haven't already signed up, then jump onto it. I'll leave a link down below as well. A lot of people have been jumping onto it now, which is really, really good to see. Some people let me know that they couldn't access the previous ones. I thought that I actually had a link in the emails that said past issues. So I'm going to work that out for this Thursday. I'm going to work on that today, actually, so that when you get the email on Thursday morning, they come out at 10 o'clock. Then there should be a link in there that says past issues now. You should be able to go back and check the back catalogue of everything that you might have missed, or just to review them so you don't have to search through your email as well. If there's particular topics that you'd like to see covered in them, I'm trying to theme them every week. Same thing, let me know with that as well. Otherwise, I will see you in the next one.